Welcome to This Explainer. I'm your host, the strategist, and today we are embarking on a massive excavation. Listen, if you want to actually master your Cambridge computer science exams, it doesn't matter if you're tackling syllabus codes 9618, 0417, 0478, 0983, 0984, or even 2210. You have to start thinking like a paleontologist on a dig. We're not just going to sweep away the surface dirt today. No, we're digging deep, deep down through the fossil layers of past paper questions. And today, our target specimen, it's an absolute beast. We're talking about Lossy compression principles and applications. Now, this topic is notorious. It is literally everywhere. It appears in almost every single examination series, and yet it constantly catches students off guard and ruins their grades. So what we're going to do is carefully excavate the layers of these multi-part Lossy compression questions, dust off all those common misconceptions you probably have right now, and reconstruct the absolute perfect examiner-approved answer from the ground up. Grab your tools, let's dive right into this and unearth some top grades.
Here is our map for today's dig. First, the Lossy Compression Challenge. Second, unearthing core principles. Third, the procedural framework. Fourth, critical analysis mastery. Fifth, top examiner warnings. And finally, number 6, the final exam strategy.
Section 1. The Lossy Compression Challenge. Digging the surface.
Okay, let's get real for a second. Lossy compression is one of those topics that creates a massive illusion of competence. It seems so incredibly simple when you read it in a textbook, right? You just remove data permanently to reduce the file size. Bam! Done. Simple. But actually, no. Wrong. When you step into the context of a Cambridge 9618 exam, it instantly becomes one of the most punishing topics for unprepared students. This is the surface-level problem of our dig today. Students genuinely think they know the material, they walk into that exam room brimming with confidence, and then they get completely blindsided by a brutal, multi-part scenario question. So I want to pose a critical question to you right now. Why do students find multi-step Lossy compression calculations so hard? Why is there such a massive, glaring disconnect between understanding the basic theory and actually scoring the marks on the paper? Well, the truth is, knowing the raw facts just isn't enough to secure the method marks. The exam board doesn't want you to just be a human encyclopedia spitting out definitions. They want a problem solver. They want to see your procedural logic on the page. If you just memorize the simple fact that JPEG is lossy and PNG is lossless, you are absolutely going to lose out on those massive 6 to 8 mark questions that demand deep computational thinking and multi-step execution.
Let me show you exactly what I mean. Let's look at a real Cambridge past paper question scenario. This one focuses on streaming high-definition audio, and we're going to look at 2 very common, entirely flawed approaches we see out in the wild all the time. On the left side of your screen, we have Alex's answer. Now, Alex is your classic over-preparer. Alex writes, Lossy compression permanently removes data. MP3 uses psychoacoustics to remove frequencies the human ear cannot hear. This reduces file size significantly. Okay, let's pause. Everything Alex just said is technically a true computer science fact. But look at all those red pen marks. Why did Alex fail? Because there is zero analysis. Alex just dumped a bunch of textbook facts onto the page without actually evaluating the impact on the specific streaming scenario that the question provided. Now look over on the right. We have Sam. Sam's answer says, use Lossy compression because the file needs to be small to stream fast. Sam completely rushes the response and entirely misses the command word requirements. The command word in this question was evaluate, which demands looking at both sides, weighing them up, and making a justified conclusion. Sam just gave a one-sided, incredibly shallow response. Both of these students completely failed to reconstruct the dinosaur. They just left a pile of scattered bones on the page.
And this brilliantly illustrates exactly what the examiners are desperately trying to tell us year after year. Look at this quote. We pulled this directly from the principal examiner report. It says, top-performing students exhibit connected, conceptual understanding transferable to unfamiliar contexts. Let that sink in. Your secret weapon for jumping grade boundaries is not memorizing more random facts. It is connecting cross-topic concepts together. Can you link the core principles of Lossy compression to network bandwidth limitations? Can you connect it to storage media architectures? Better yet, can you apply those principles to a completely unfamiliar, weird context, like compressing telemetry data from a deep-sea submarine? The examiners are practically begging you to show that you understand how this technology actually interacts with its environment in the real world.
Section 2. Unearthing core principles. The strategy reveal.
All right, it is time to peel back that first fossil layer. We really need to decode the specific assessment objectives for Syllabus 9618, and to do that, we have to understand command words. Words like analyze, evaluate, compare, and discuss are not just polite suggestions from the examiner. They are strict, structural, non-negotiable requirements for exactly how you must build your answer. If the command word is compare and you only write about one thing, your mark is capped instantly. No exceptions. We need a reliable framework to guarantee we hit these objectives every single time we put pen to paper. Enter the PEAL framework. Point, evidence, explanation, link. This is the absolute essential structure for constructing top-tier analytical computer science answers, and let me tell you, it is the absolute cure for multi-step theory questions. Here is exactly how top candidates use it. First, the point. You make a clear, direct statement answering the prompt. For example, lossy compression is highly suitable for this audio streaming platform. Boom, direct. Second, the evidence. This is where you bring in a hard technical fact, because it utilizes perceptual coding algorithms to permanently remove inaudible frequencies. Third, the explanation. You detail the mechanism or the consequence of that evidence. This drastic reduction in bit depth significantly lowers the required bandwidth for transmission. And finally, the most important part that everyone forgets, the link. You tie it all back to the specific scenario they gave you. Consequently, users with slower mobile networks will experience less buffering during live playback. Do you see how powerful that is? Point, evidence, explanation, link. It is a completely foolproof system.
Before we continue, subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, are you ready? I'm giving you a 30-second interactive challenge. I'm going to put 2 paragraphs on the screen in a moment, and I want you to spot which one correctly applies the PEAL framework to a lossy compression algorithm scenario. I want you to actively look for the point, look for that technical evidence, trace the explanation, and aggressively search for that link back to the context.
Section 3, the procedural framework, method mark strategy.
Time is up! If you focused on the paragraph that explicitly mentioned the scenario-specific constraints, you absolutely nailed it. Now, we're going to shift gears from theory into technical methodology. We are looking at data interpretation and programming skills. When you are hit with a calculation question in lossy compression, say calculating the new file size of an image after a 10-to-1 compression ratio is applied, you need to understand something crucial. The final number you get is only worth a fraction of the total marks. The actual magic lies entirely in the method. Here is the step-by-step procedure examiners are desperately looking for when they grade your paper. Step 1. Extract from binary representations. You must explicitly write down the values you are pulling from the question. If the header file is given to you in hexadecimal, convert it to binary and write that exact step down on the paper. Show the examiner you know what raw data you are working with. Step 2. Perform calculations. Write out the full formula. Listen to me on this one. Even if you punch the wrong number into your calculator because you're stressed, if your written formula is correct, say, multiplying resolution by color depth before applying the compression ratio, you secure the method marks. The process of decompression or compression is what's actually being tested here, not just the final number. Step 3. Draw evidence-based conclusions. Don't just leave a naked number dangling at the bottom of the page. State what that number means for the entire system. Write something like, therefore, the 2 megabyte file is reduced to 200 kilobytes, allowing it to easily fit within the 500 kilobyte email attachment limit. Let's dramatically contrast this with a live 60-second interactive rewrite. Watch the red marks on your screen transform into green checks. First, we have the generic classic mistake. The student writes, lossy compression reduces file size by removing redundant data, making it faster to download. Red pen everywhere. Why? Because it's just a generic textbook definition floating in the void. It has no home. Now, watch the top-tier reconstruction down on the bottom. In the context of the hospital's MRI archiving system, while lossy compression significantly reduces server storage requirements, it is inappropriate because the permanent removal of high-frequency pixel data could result in medical misdiagnosis. Boom. Green checks across the board. Look at what we did. We directly applied the compression principles to the specific, localized scenario of a hospital MRI machine. We linked the technical action, removing pixel data, to the massive real-world consequence, medical misdiagnosis. That right there is exactly how you get full marks. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @Ace the Exams IGCE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 4. Critical Analysis Mastery. Interactive Workshop. Welcome to our interactive workshop. I need your absolute active participation right now. Do not just watch this passively. High-level evaluation and comparative analysis require active mental lifting. In computer science, you are constantly going to be asked to compare approaches, like comparing lossy versus lossless compression for a very specific data type. This matrix you see on screen is your ultimate blueprint for the perfect comparative answer. Let's run a quick data scan and speedwriting challenge. Imagine a scenario comparing compressing a text-based source code file versus a high-resolution photograph. First, similarities. Both algorithms aim to reduce the overall file footprint to optimize storage. Simple. Second, differences. This is where you contrast approaches using comparative connectives. You'd say, whereas lossy compression permanently discards data, conversely, lossless compression relies on statistical redundancy to ensure exact bit-for-bit recreation. Third, evidence. You've got to back it up with technical facts. For instance, running a lossy algorithm on source code will destroy syntax, rendering the entire program uncompilable. Finally, conclusions. Justify your recommendation based on the evidence. Therefore, lossless is mandatory for the source code, while lossy is optimal for the photograph where perceptual quality remains acceptable to the human eye. If you build your paragraphs using this exact table structure in the exam, you are guaranteed to hit those elusive higher-order assessment objectives.
Section 5. Top Examiner Warnings, the fossils of past papers.
Now, we are transitioning to the absolute most critical part of our entire dig today. We are going to analyze the remains of past mistakes. And listen, these aren't just my opinions. These are direct, literal quotes pulled from the principal examiner reports. These are the fatal traps that thousands of smart students fall into every single year. Let's start the countdown of the top 3 fatal mistakes. Coming in at number 3, confusing cause and effect in lossy compression principles. Examiners repeatedly report that students get the technical mechanisms entirely backwards. For example, a stressed student might write down that reducing the file size causes the compression algorithm to run. No! The compression algorithm, like applying a discrete cosine transform to an image file, is the cause, and the reduction in file size is the effect. Or they confuse the artifacting process, thinking that the pixelation causes the data loss rather than the data loss causing the visual pixelation on your screen. You absolutely must have your causal relationships meticulously defined in your head before you write a single word.
Coming in at number 2, forgetting to check boundary conditions in edge cases during algorithmic testing. When you are writing or analyzing pseudocode for a compression algorithm, students almost always focus purely on the happy path. What happens when everything works perfectly normally? But examiners want to see true algorithmic thinking. What happens if the image being compressed is pure white? Does the run length encoding fail? What happens if the file being compressed is already highly compressed? Will running a lossy algorithm actually increase the file size because of the new header overhead? If you don't explicitly mention these boundary conditions in your evaluation, you are leaving massive marks on the table for no reason.
And finally, the number 1 ultimate examiner alert, the single biggest fossil we find buried in the exam hall. Providing generic answers that completely ignore the question's specific context. I literally cannot stress this enough. If the exam question asks you about a bank transferring highly sensitive financial records and you write a brilliant, technically flawless, beautifully worded essay about how lossy compression is great for streaming YouTube videos, you will score 0 marks for context. None. Your answer must live and breathe inside the scenario they give you. You have to link every single technical point back to the given environment. That is the ultimate, undeniable secret to mastering Cambridge computer science. Section 6. The final exam strategy. Reconstructing the dinosaur.
All right, we have excavated all the pieces. We deeply understand the theory. We have the Peel framework locked in. We know exactly how to secure method marks, and we know exactly what traps the examiners have set for us in the dirt. Now, here's your definitive computer science success blueprint. I want you to memorize this checklist. First, deconstruct the question. Highlight the command word immediately. Is it analyze, evaluate, or state? This one word dictates your entire structural approach. Second, extract relevant data. Pull the specific numbers, the file types, and the scenario constraints directly out of the text and write them down. Third, select the analytical framework. Ask yourself, are you using Peel for a heavy theory question or the method mark strategy for a multi-step calculation? Fourth, execute with clear notation. Show your working, show your conversions from binary to denary, and lay out your steps logically so the examiner can follow your brain. Fifth, present with correct terminology. Do not ever say it makes the file smaller. Say it reduces bit depth. Do not say, "It looks worse." Say, "It introduces visual artifacts." Applying this system systematically is exactly how you avoid the tragic pitfalls of Alex and Sam that we saw at the very beginning of this dig.
The social proof is right here in the grading data. When we look at students who just wing it, the average candidate, they hover around a C or maybe a B. But look at bar 2. Just implementing the PEL framework alone pushes that up significantly. And bar 3, students who consistently implement this full exact framework see a massive +2 grade boundary improvement, from a C to an A or a B to an A star. It is entirely possible, but it requires systematic, structured thinking. It's about playing the exam game perfectly. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep digging, keep practicing, and I will see you in the next explainer.